Hello and welcome to Section 8, Score-Based Algorithms, Tree-Structured Networks. In the previous section, we saw a number of techniques to simplify the learning procedure. One of the ways to speed up the search procedure is to limit the search space. Tree-structured networks provide a simple search space. What is a tree-structured network? A DAG-G is a tree-structured network if for every variable x, there is at most one parent in the DAG. So parents of x is less than or equal to 1. Note that tree-structured networks are not necessarily trees, meaning that they're not necessarily connected, but they can be a collection of unconnected trees. Like here, there's no link between these two trees. Okay, but the point is that this is not necessarily a directed forest because you may have parents of size greater than 1. Here you cannot have that. Note that tree-structured networks factorize the joint probability into marginal probabilities and first-order conditional probabilities, like P of xi and P of xi condition on xj. And this is an example. It's the factorization according to this graph. So you see only first-order terms and zero-order terms are appearing. Now, the good thing about tree-structured networks is that V-structures don't appear. And this means that same skeleton implies I equivalence. But why V-structures don't appear? Because the parent size is limited to 1. So this means that under score equivalence, if we use a score that satisfies it, we need to find only the optimal skeleton. And to see an example, the following two tree structures, they have the same skeleton, but different edge orientations. But both have the same likelihood score. If we calculate it according to this table, we see that they have the same score. And this obviously follows the score equivalence that we saw in the previous sections. Okay, how does this whole tree structure restriction affect the computational cost? Well, let's see. Consider the score difference of an arbitrary G to the empty network G empty or GO. And this is basically a graph without edges. So I construct delta G as follows, the difference of the scores. Note that the graph that maximizes delta G also maximizes the score. This is just, we will see the usage of this. It will simplify our calculations when we take this subtraction. Okay, so I have this difference. If we decompose the scores into family scores, then the nodes without a parent in G cancel out. Okay, so this graph has no parents. And here, if there's a node without a parent, then they just cancel out. So this will simplify to the following term. It will be the summation over the family scores of xi and its parents minus family score of xi without a parent. But then the parents is at most 1, if not empty. So this is basically just some other node xj. So you can see that then delta G is basically some wg to I, which I'm considering it as a weight. So I'm renaming this family score difference as wg to I, and then delta G will be this summation. So by defining this term as the difference in the family scores of node xi with and without xj as its parent, then we have that delta G can be written as the summation of the weights over all the edges in G. Wji can be thought as a weight associated to the edge j to I, then delta G would be the total weight of the graph G. And this means that my problem to maximize delta G is essentially equivalent to finding the maximum weight spanning tree structure G in the weighted fully connected graph over all variables. So again, I want to maximize this term. What is this? Well, if I consider the fully connected network over all of the variables, here you see that there's two edge There are two edges connecting every two node. Okay. Now, if I consider this graph, I want to construct a tree-structured network that spans the vertices, and it should have the maximum weight. So like here, for example, we see that x4 to x5 is 9. Can I connect x4, for example, to x1? No, because it has then this weight has a negative value. Also this one, also this one. So this should be really separate. Can I reverse this edge? No, because 9 is greater than 3. We can't always deal with the problem in a local manner, but the good thing is that this problem can be solved in polynomial time. Okay, so I can find the optimum tree in polynomial time. The problem actually becomes simpler under score equivalence, as then we have that the weights are equal in both directions, and we only need to find the skeleton. We just discussed that. And the reason is because then once you have the skeleton, you can add the directions by taking a random node as the root and directing the edges away from it. It doesn't matter which node, just one node as the root. Note that tree structure network, it's basically it's a forest, a collection of trees. We already discussed that. So if we limit the networks to connected ones, then the problem becomes that of finding a maximum spanning tree. Just to provide a formal definition, for a connected weighted graph G, here we consider the fully connected graph, the maximum weight spanning tree consists of the subset of edges having the maximum total edge weight and connecting all the nodes in G without any cycle. Okay, so here, for example, the maximum spanning tree will be this. Another interpretation is that a maximum spanning tree is a spanning tree whose total weight is as large as possible. Okay, back to our algorithm. The problem of finding the G with the max score is translated as the maximum spanning tree or the forest. This algorithm, this whole approach is actually also known as the Chu-Liu algorithm. And what is the complexity? Well, the algorithm for finding maximum spanning tree has complexity O(n) squared log n, and it also takes O(n) squared times capital N, the size of the data, to obtain all of the weights. So overall, it takes O(n) squared times capital N plus log of n to perform this algorithm. Great. What are the benefits of using a tree structure? Is it just because they make it simpler? Well, that is one reason. Tree structures are simple and avoid the overfitting problems that happen with complex structures. We can almost be assured that overfitting will not happen. And they also capture the most important independencies because their number of edges is limited. Finally, they are also relatively fast to train and hence serve as a baseline for learning more complex structures. To summarize, the question is how we can decrease the computational costs in score-based algorithms, and one approach was to limit the search space to tree-structured networks. That means that such networks that have cycles, they are not accepted anymore, and therefore the next high score network in a form of a tree structure will be accepted. Okay, thanks for your attention.